Swayam Prabha. Digital India. Educated India.
So, in continuation of regression, next we have to move to the estimating the noise variance. We assumed that the noise variance sigma square is known. However, we can also use the principle of maximum likelihood estimation to obtain the likelihood estimator sigma maximum likelihood square for the noise variance. To do this, the following standard procedure: we write down the log likelihood, compute its derivative with respect to sigma square is positive. So, it to be 0 and solve. So, the log likelihood is given by log of p of y over x comma theta comma sigma square, which is equal to summation n varies from 1 to n log of n yn by phi transpose of xn into theta comma sigma square, which is equal to summation n equal to 1 to n minus 1 by 2 into log of 2 pi minus 1 by 2 log sigma square minus 1 by 2 sigma square of yn minus phi transpose of x1 into theta the whole square. So, further simplify. So, it becomes minus n by 2 into log sigma square and 1 by sigma square into summation y minus phi transpose of x1 theta the whole square plus constant will come. So, the partial derivative of log of likelihood with respect to sigma square is dou by dou sigma of square of log of p of y over x of theta comma sigma square is log of sigma square 1 by sigma square into 2 sigma and then it become minus n by 2 sigma square, and this one is minus 1 by 2 sigma square of s, and this becomes 0, therefore equating them, therefore n by 2 sigma square equal to s by 2 sigma power 4. So, we identify that maximum likelihood of sigma square is equal to s by n, which is equal to 1 by n into summation n varies from 1 to n yn of phi transpose x1 into theta the whole square. Therefore, the maximum likelihood estimate of the noise variance is the empirical mean of the square distance between the noise free function value phi transpose of xn theta and the corresponding noisy observation yn at input location xn. Next, to overfitting in a linear regression, we just discussed how to use the maximum likelihood estimation to fit linear model, example the polynomials to data. So, we can evaluate the quality of the model by computing the error or loss incurred. One way of doing this to compute the negative log likelihood, which we minimize to determine the maximum likelihood estimator. Alternatively, given that the noise parameter sigma square is not a free model parameter, so we can ignore the scaling by 1 by sigma square, so that we end up with a square error loss function of norm of y minus phi theta square. So, instead of using the squared loss, we often use the root mean square of RMSE. So, 1 by root of 1 by n norm of y minus phi theta square equal to root of 1 by n to summation n equal to 1 to n yn minus phi transpose xn into theta the whole square. So, two cases: A allows us to compare error of data sets with different sizes, and B has the same scale and the same unit as observed functions yn. For example, if you fit a model that maps postcodes values of yn, for example, if you fit a model that maps postcode X is given in the latitude and longitude to house prices Y values are EUR. Then the RMSE is also measured in EUR, whereas the squared error is given by EUR square. So, if you choose to include the factor sigma square from the original negative likelihood, then we end up with a unitless objective. That is, in the preceding example, our objective would no longer be in EUR or EUR square. So, that is the meaning of overfitting in a linearly regression. So, based on the root mean square error or squared error like that. So, the model in the C is this section. We can use the RMSE, negative log likelihood, to determine the best degree of the polynomial by finding the polynomial degree m that minimizes the objective. Given that the polynomial degree is a natural number, so we can perform a brute force search and enumerate all reasonable values of m. For a training set of the size n, it is sufficient to test m lies between 0 to n minus 1. For m is less than n, the maximum likelihood estimator is unique. For m greater than or equal to n, we have more parameters like likelihood fit for different parameter, different polynomials degrees in m. So, m equal to 0, the blue line represent the MLE, maximum likelihood, and plus stands for training data, and based on the result of m equal to 1, and we have a slightly start from 1 to 4.5 or 5 like that, and we have a lightly the modified in m equal to 3 in the curve, and m equal to 4 the sine and cos associated, m equal to 6 also the curve like this, and m equal to 9 we have a disjoint of at between minus 4 to 4 and minus 4 to 2 minus 2, and start from minus 1 to end we have a curve of a sine and cosine. So, it means the maximum likelihood occurred corresponding to the values of m. So, these are all the demonstration of the pictures, that data points, and we need to solve the undetermined system of the equation of 19th equation phi transpose phi. So, this also no longer be invertible, so that there are infinitely many possible maximum likelihood estimators. So, figure 9.5 shows that the number of polynomial fits is determined by maximum likelihood for the data set of figure 9.4a with n equal to 10 observation. So, the notice the polynomial of low degree constant m equal to 0 or m equal to 1, and it fit the data poorly, hence or poor representation of the true lying underlying fictions, and m varies from 3 to 6, the fit look plausible and smoothly interpolate the data, and when we go to a higher degree polynomial, we notice that they fit the data better and better. So, in the x polynomials we notice that they fit the data better and better. In extreme case, when m equal to 9, that is n minus 1 equal to 9, the function will pass through the every single data point. However, these higher degree polynomial oscillate widely and are poor representation of underlying the function that generated the data, such that we suffer from overfitting. So, looking now at the test error, which is a qualitative measure of generalization properties of corresponding polynomial, we notice that initially the test error decreases, and see the figure 9.6 is a training as a test error, or that orange color shows that the degree of the polynomial. For the fourth order polynomial, the test error is relatively low, and stays relatively constant up to the degree 5. So, the blue curve shows that the training error and never increases when the degree of the polynomial increases. So, the best generalization is to obtain the polynomial of degree 4. However, from the degree 6 onward, the test error increases significantly, and high order polynomials have very bad generalization properties. In particular example, this is also evident from the corresponding the training error and test error of the polynomial of the degree 6 as well as degree 5 and the polynomial of degree m equal to 4. Next, we have a maximum posterior estimation. We just saw that maximum likelihood estimation is prone to overfitting. So, we often observe that the magnitude of the parameter value becomes relatively large if we run into overfitting. To mitigate the effect of huge parameter values, we can place a prior distribution on the parameter. So, the prior distribution explicitly encode what parameter value are plausible before having seen any data. For example, the Gaussian prior P of theta equal to n of 0, 1 on a single parameter theta encodes that parameter value or expected lie in the interval -2 to 2, and we have as two standard deviation around the mean value once a data x and y are available. Instead of maximizing the likelihood, we seek the parameter that maximize the posterior distribution P of theta by x, y. This procedure is called maximum posterior estimation. So, the posterior over the parameter theta giving the training data x and y is applied by Bayes' theorem with the help of the conditional probability P of theta by x, y equal to P of y by x, theta into P of theta by P of y by x. Since the posterior explicitly depends on the parameter prior P of theta, the prior will have an effect on the parameter vector we find as the maximizer of the posterior. So, we will see that more explicitly in the following. So, the parameter vector theta map that maximize the posterior is map estimate. So, to find a map estimate, we follow steps that are similar in flavor of to maximum likelihood estimation. We start the log transformation and compute the log posterior. Therefore, log of P of theta by x, y equal to log of P of y by x, theta plus log of P theta plus constant, where the constant comprises the term that are independent of theta. So, we see the long posterior in the equation 25 is the sum of the log likelihood P of y over x, theta and the log prior of log P of theta, so that the map estimate will be compromise between the prior. So, our suggestion for plausible parameter values before observing data and data dependent likelihood. So, to find the map estimate is theta map. So, we minimize the negative log posterior distribution with respect to theta, and we solve theta map belongs to argument of minimum of minus log P of y over x, theta minus log of P of theta. So, the gradient of negative log posterior with respect to theta is minus d by d theta of log of P of theta by x, y minus d by d theta of log of P of y over x, theta, which is equal to minus d of log P of theta by d theta. Now, we identify the first term on the right hand side as the gradient of the negative log likelihood from the equation 11c. So, with the conjugate Gaussian prior P of theta is n of theta comma b square I on the parameter theta, and negative log posterior for the linear regression setting in the equation 13 we obtain the negative log posterior. Therefore, minus log of P of theta by x, y equal to 1 by sigma square into y minus phi of theta whole transpose into y minus phi theta plus 1 by 2 b square into theta power t into theta plus constant. So, here the first term correspond to the contribution from the log likelihood. So, the second term originate from log prior. So, the gradient of log posterior with respect to the parameter theta is given by minus d by d theta of log of p of theta over x comma y equal to 1 by sigma square, because differentiate with respect to theta. So, 1 by sigma square into theta power theta transpose into phi transpose into phi minus y transpose phi plus 1 by b square theta transpose. So, we will find the map estimate, that is theta by theta suffix map, by setting the gradient to theta 0 and solving theta map. We obtain 1 by sigma square into theta transpose into phi minus y transpose phi plus 1 by b square theta transpose equal to 0. Therefore, bring 1 by sigma square one side and or theta transpose take it outside. So, theta transpose into 1 by sigma square phi transpose phi plus 1 by b square I, and then bring this one here. So, 1 by sigma square y transpose phi equal to 0. Therefore, theta transpose into phi transpose phi and sigma square take it outside and cancel it. Therefore, sigma square by b square into I equal to 1 by y transpose phi. Therefore, theta transpose equal to y transpose phi into phi transpose phi plus sigma square by b square into I the whole inverse, because we have to bring this side. So, this is the map estimate, and theta map is phi transpose phi plus sigma square by b square into I whole transpose phi transpose y. So, comparing map estimate with the maximum likelihood estimate, we see that only the difference between both the solution is additional term of sigma square by b square I in the inverse matrix. So, this term ensures that phi transpose phi plus sigma square b square I is a symmetric and strictly positive definite. So, its inverse exists and map estimate the unique solution of the system of linear equation. Moreover, it reflects the impact of the regularizer. Next example, map estimation for polynomial regression. In the polynomial regression example from the section, we place a Gaussian prior p of theta equal to n of 0 comma I on the parameter theta and determine the map estimate according to the equation 31. In figure 9.7, we show both the maximum likelihood and the map estimate for the polynomial of degree 6 and degree 8, and does not play any significant role for the low degree polynomial, but keeps the function relatively smooth for higher degree polynomials. Although the map estimate can push the boundaries of overfitting, it is not a general solution to this problem. So, we need a more principled approach to tackle the outfitting. So, this is the figure of 9.7 of a polynomial of degree 6 and a polynomial of degree 8, and maximally likelihood and map also mentioned in the yellow color, and training data is a plus denote. This is a polynomial regression of maximum likelihood, and the polynomial of degree 6 and 8 respectively A and B the picture shows. Next, map estimation as a regularization. Instead of placing a prior distribution of a parameter theta, it is also possible to mitigate the effect of outfitting by penalizing the amplitude of the parameter by means of regularization. So, in regularized least square, we consider the loss function norm of y minus phi theta square plus lambda into theta norm of theta 2 in the 2-dimensional effect. So, which we minimize the respect to theta. Here the first term is a data fit term and it is called as a misfit term, which is proportional to negative likely loghood. The second term is called the regularizer, and the regularizer parameter lambda greater equal to 0, which control the strictness of the regularization. And note, instead of Euclidean norm, we can choose any p norm. In practice, smaller values of p lead to sparser solution. Here, sparse means that many parameter value theta d equal to 0, which is also useful for variable selection. For p equal to 1, the regularizer is called a lasso, least absolute shrinkage and selection operator, and was proposed by Zipstrani. The regularizer of lambda of norm of theta square in the equation 32 can be interpreted as a negative log Gaussian prior, which we use the map estimation, and the equation 26c, more specifically the Gaussian prior p of theta equal to n of 0 comma b square I, we obtain the negative log Gaussian square of minus log of p of theta equal to 1 by 2 b square into norm theta square plus constant. So, lambda equal to 1 by 2 b square, the regularization term and negative log Gaussian prior are identical. So, given that the regularized least square loss function consists of terms that are closely related to negative log likelihood plus negative log prior, it is not surprising that when we minimize this loss, we obtain the solution that closely resemble that map estimates in 31. More specifically, minimizing the regularized least square loss function yields theta RLS equal to phi transpose phi plus lambda I the inverse into phi transpose y, which is identical to map estimate for lambda equal to sigma square by b square, where sigma square is a noise variance and b square is a variance of Gaussian prior is isotropic, and p of theta equal to n of 0 comma b square I. So, we have a covered parameter estimation using maximum likelihood and map estimation, where we found a point estimate theta star that optimize an objective function. So, we saw that both the maximum likelihood and the map estimation can lead overfitting. Now, Bayesian linear regression. So, Bayesian linear regression pushes the idea of a parameter priori a step further and does not even attempt to compute a point estimate of the parameters, but instead the full posterior distribution over the parameter is taken into account when making predictions. This means we do not fit any parameters, but we compute a mean over all plausible parameter settings according to the posterior. Now, we have a model. In Bayesian linear regression, we consider the model prior is p of theta equal to n of m naught comma s naught, and likelihood p of y bar x comma theta is n of y bar theta transpose x into theta comma x square sigma square, where we now explicitly place a Gaussian prior p of theta equal to n of m naught comma s naught on theta, which turns the parameter vector into random variable. This allows us to write down the corresponding graphical model in the figure 9.8 is a Bayesian linear regression, and where we made the parameter of the Gaussian prior on theta explicit. So, the full probabilistic model joint distribution unobserved random variable y and theta respectively p of y of theta bar x equal to p of y bar x comma theta into p of theta. Next, prior prediction. In practice, we are usually not so much interested in the parameter value theta themselves. Instead, our focus often lies in the prediction we made with those parameter values. In a Bayesian setting, we take the parameter distribution and average over all plausible parameter settings when we make prediction. More specifically, to make a prediction at an input x, we integrate out theta and obtain p of y over x equal to integral p of y over x comma theta into p of theta d theta equal to e theta of p of y over x comma theta, which we can interpret the average prediction y by x comma theta for all plausible parameter theta according to the prior distribution p of theta. Note that prediction using prior distribution only require us to specify the input, but no training data. So, in our model we choose a conjugate prior on theta. So, the predictive distribution is a Gaussian as well. With the prior distribution p of theta equal to n of m naught comma s naught, we obtain the predictive distribution as p of y star bar s star, which is equal to n of phi transpose x star into m naught, comma phi transpose of x star s naught and phi of x plus sigma square. So, where we exploited that, number 1, the prediction is a Gaussian due to conjugacy and marginalization property of Gaussian. Number 2, the Gaussian noise is independent, so that V of y star equal to V of theta of phi transpose x theta plus V epsilon, and 2, y star is a linear transformation of theta, so that we can apply the rules for computing the mean and the covariance of the prediction analytically. Analytically using 50 and 51 respectively. In 38, the term phi transpose of x star s naught of phi of x star in the predictive variance explicitly accounts for the uncertainty associated with the parameter theta, whereas sigma square is uncertainty contribution due to the measurement noise. So, if we are interested in predicting noise free function value f of x star is equal to phi transpose x star theta instead of noise corrupted targets y star, we obtain P of f of x star equal to n of phi transpose x star m naught, phi transpose of x star into s naught of phi of x naught. So, which only differs from the equation 38 in the omission of the noise variance sigma square in the predictive variance. Note, so the distribution over function, since we can represent the distribution phi of theta using a set of samples theta I, and every sample theta I gives rise to a function f of I, which is equal to phi transpose into phi dot. So, it follows that parameter distribution p of theta induces distribution of p of f of theta f of dot over function. However, we use the notation dot to explicitly denote the functional relationship. So, this is the graph that represent the prior over function. So, the first one says that the between the prior, and second one is a sample from the prior distribution over the function. So, the picture represent in terms of phi of theta equal to n over 0 comma 1 by 4 phi. So, this is the polynomial of degree 5, and this induces the pair of distribution and over the function, and this shaded area is dark grey is a 67% confidence bound, and light grey is a 95% confidence bound, and this includes some function of the sample from this prior, and the function sample is obtained first sampling a parameter vector theta is approximately equal to p of theta, and we have to compute fi of dot. Fi dot is a functional mapping, that is theta I transpose into phi of I, and we used 200 input location in the area of minus phi to phi, and this is the future functions. This uncertainty of the representation of shaded area is solely due to the parameter because we consider noise free predictive distribution. That is the demonstration of the above figure. Now, we looked at the computing prediction using the parameter PR theta, and we have a parameter posterior. So, the sample principle for prediction and inference hold. We just need to replace the prior p of theta and the posterior p of theta bar x comma y. In the following, we will derive the posterior distribution in the detail before using it to make prediction. So, the posterior distribution is given a training set of input xn in Rd and a corresponding observation yn in R, where n varies from 1 to n, and compute the posterior over the Bayesian function b of theta over x comma y is equal to p of y over x comma theta into p of theta by p of y over x, and where x is the training input and y is a collection of corresponding training targets, and p of y by x comma theta is a likelihood, and p of theta is a parameter, and we have a p of y over x equal to integral p of y over x comma theta into p of theta d theta is expectation of p of y over x comma theta, So, this is the marginal likelihood evidence which is independent of parameter theta and ensure that the posterior is normalized and it is integrate to 1. So, the marginal likelihood as a likelihood average over all possible parameter settings with respect to the prior distribution of P of theta. So, by theorem parameter posterior in our model 35, the parameter posterior model 41 can be computed and closed form is P of theta by x comma y equal to n of theta over mn comma Sn, where Sn equal to S naught inverse plus sigma square minus 2 into phi transpose phi whole inverse. So, mn equal to Sn of S naught of inverse m naught plus sigma minus 2 into phi transpose y, where the subscript n indicates the size of the training set. So, let it be 43 for A, B, C denoted, and by according to the Bayes theorem, the posterior P of theta by x of y is proportional to the product of likelihood P of y over x comma theta and prior P of theta. So, the posterior is Bayes theorem P of theta by x comma y equal to P of y over x comma theta into P of theta by P of y over x is 44a, and the likelihood is P of y over x comma theta is n of y in by phi of theta comma sigma square I denoted by 44b, and prior is P of theta equal to n by m naught comma S naught is 44c. So, instead of looking at the product of the prior and the likelihood, we can transform the problem into log space and solve for the mean and covariance of the posterior by completing the squares. So, the sum of the log prior and the log likelihood is log of n of y by phi theta comma sigma square I plus log of n of theta by m naught comma S naught, therefore, which is equal to minus 1 by 2 into sigma minus 2 y minus phi theta transpose into y minus phi theta plus theta minus m naught transpose into S naught inverse of theta minus m naught plus constant. So, where the constant contains the terms independent of theta. So, we will ignore the constant in terms of the following. So, we factorize 45b which yield minus 1 by 2 into sigma square y transpose y minus 2 sigma power minus 2 into y transpose phi theta plus theta transpose into sigma power minus 2 into phi transpose into phi theta plus theta transpose to S naught inverse theta minus 2 m naught t S naught inverse theta plus m naught t S naught minus m naught. So, which is equal to minus half into theta transpose into sigma power minus 2 phi transpose phi plus S naught minus theta minus 2 into sigma power minus 2 phi transpose y plus S naught inverse m naught whole transpose theta plus constant, where the constant contains the black terms which are independent of theta. So, the orange terms are terms that are linear in theta, and the blue terms are the ones that are quadratic in theta. Now, inspecting 46b, we find that this equation is a quadratic in theta. So, the fact that unnormalized long posterior distribution is a quadratic form implies that the posterior is a Gaussian. Therefore, P of theta over x comma y equal to exponential of log of P of theta by x comma y is proportional to exponential of log of P y over x comma theta plus log of P theta, which is proportional to exponential of minus half into theta transpose into sigma power minus 1 minus 2 into phi transpose phi plus S naught inverse into theta minus 2 into sigma power minus 2 phi transpose y plus S naught inverse m naught transpose of theta, and this represents 47b. So, where we used 46b in the last expression, it satisfies, therefore, that is P of theta over x by comma y. So, the remaining task is to bring the unnormalized Gaussian into the form of the proportional to n of theta over mn comma Sn. So, we need to identify the mean mn and the covariance Sn. So, to do this, we use the concept completing the square. The desired log posterior is log of n of theta by mn comma Sn equal to minus half into theta minus mn transpose into Sn inverse to theta minus mn plus constant, which is equal to minus half into theta transpose to Sn inverse theta minus 2 mn transpose Sn minus theta plus mn transpose into Sn power minus 1 mn. Here we factorize the quadratic form theta minus mn transpose Sn inverse theta minus mn into a term that is quadratic in theta alone, that represent the blue. A term that is linear in theta is orange and a constant term is a black. So, this allows us now to find Sn and Mn by matching the colored expression in 46b and 48b. So, this yield Sn inverse is phi transpose sigma power minus 2 into I into phi plus S naught inverse, if and only if Sn equal to sigma power minus 2 into phi transpose phi plus S naught inverse the whole inverse. Therefore, Mn transpose into Sn inverse is equal to sigma power minus 2 into phi transpose y plus S naught inverse into m naught whole transpose. Let it be 50a, if and only if Mn equal to Sn into sigma power minus 2 phi transpose y plus Sn inverse of m naught is represent 50b. So, this is the meaning of corresponding unnormalized Gaussian into the form of the proportion of n of theta by Mn of Sn. So, we have a note, the general approach to complete the square. If we are given the equation x transpose Ax minus 2 A transpose x plus constant, where A is a symmetric and positive definite, which we wish to bring into the form of x minus mu transpose into summation x minus mu plus constant. So, we can do this by setting summation equal to A and mu equal to summation inverse A and constant T2 equal to constant T1 minus mu transpose summation mu. So, we can see that the term inside the exponential 47b are of the form 51. Therefore, A equal to sigma power minus 2 into phi transpose phi plus S naught inverse is 55 and A equal to sigma power minus 2 into phi transpose y plus S naught inverse m naught is 56. Here capital A and small a can be difficult to identify the equation 46a. It is often helpful to bring these equations into the form 51. So, that decouples the quadratic form, linear terms and constant, which simplify finding the desired solution.